All right. Good afternoon, everyone. Welcome to NY-GEO. My name is Sanchez. I'm a mechanical engineer with CHA Consulting. Very honored today to be moderating a fantastic panel on hybrid thermal energy networks. I'm joined today by 4 industry professionals who are going to share their own experiences and design philosophies around hybrid systems. So please join me in welcoming the 4 panelists here today. We've got Sam Gerber of CDM Smith, Michael Barbasch from LaBella, Joe DiSanto from Ramboll, and Adam Shelly from Ecosystem. So please a round of applause for them. Thank you, and gentlemen, thank you for being here today. We're going to go ahead and get started. Sam is going to start us off. Thanks, Sam.
Okay, good afternoon all. So my name is Sam Gerber. I'm with CDM Smith. So CDM Smith as a whole, we're a global engineering firm, do engineering and construction in a wide variety of practices and disciplines, water, wastewater, environmental, energy, and transportation. Myself specifically, I work with our MEP and energy group, and have been lucky enough over the past 5 or 6 years to be working on a wide variety of geothermal projects, ranging from single buildings here in New York, 1515 Surf, 1 Java, to larger district energy systems, Con Edison's Mount Vernon U10, and our Vernice development in the Rockaways. So to kind of kick off this discussion, I'll launch into a little bit about why we want to hybridize and sort of the problem that we're trying to solve with it and our issues with thermal balance. So when we look at any kind of new build or retrofits, generally our goal with buildings is we're always trying to make them more efficient, higher performing, tighter. And what we find when we do that is that these buildings, those energy efficiency measures tend to have a higher impact on our heating loads than our cooling loads. So for example, here we have, this is a graph of one of our projects here in New York, where we were looking at, so a baseline code compliant building would use about twice as much heating as it does cooling. And then once you add in all of these energy efficiency measures that we have listed, you'll find that that heating load goes from 2x to about 1.4 times that cooling load. So we're moving away from heating dominance, inching towards cooling dominance. When we start to look at using a ground source heat pump system, or any kind of heat pump system, you then have to factor in heat of compression into this. Once you account for that compressor energy, you're going to move from a building, like we said before, is about 1.4 times the heating of cooling. Now you're actually going to be taking 20% more energy, putting it into the ground than you're pulling back out. The reason we have a problem with that, year over year, ground temperature won't stay constant. You'll have what we call a thermal drift, a runaway, that will negatively impact your heat pump efficiencies, and if you let it go on too long, you can lock out your compressors. We have a wide range of ways to deal with this. In particular, talking about thermal energy networks, obviously you can try to find different end users, try to balance your loads that way, getting more heating dominant as opposed to cooling dominant, or vice versa. You can expand your bore fields to try to lose more energy out the side of the bore fields. But really what we're here today to talk about is hybridizing the system to solve that problem. So when we talk about a hybrid system, we are saying non-geothermal thermal resources. This could be a wide range of things, as the rest of the panelists are also going to talk about. Anything with BTUs, we can use it. Generally, this is the most simple and basic form of a hybrid system is this kind of peak operation scheme. So what you'll do is track the condenser water temperature in your system. Whenever you find that that condenser water is moving outside of a range, whether that be high or low, you'll kick on some form of on-demand thermal resource, whether that's a boiler, whether that's a chiller, whether that's a dry cooler, and you'll bring that temperature back into the range that you want it to be. So for an example of this is a project that we've worked on here in New York. This is a hotel in Bushwick, currently under construction. We had limited space for geothermal boreholes on site. We were maxed out for what we could do for the size of our system. So to get around the cooling dominance of that system, we installed a system of 8 air source reversible chillers. And what those will do is they will monitor the condenser water temperatures And when they get out of bounds, those will kick on, bring it back in. That essentially freezes that thermal drift at whatever it is at that specific year, and you won't have that year-over-year runaway. Another kind of salient benefit to that is this gives us the flexibility for if programming ever changes in the future at this hotel. It's changed a couple times in construction. This gives us the flexibility without having to go and drill more boreholes that we don't have space for. We can always just change how often those chillers operate to keep our system working. Another way to look at this, and another potentially more efficient way to look at this, is to do it for, we call it winter operation. This would be for a cooling dominant system, but it's really more of a peak shifting as opposed to a peak shaving. This is where, so if you have some type of hybrid thermal resource that relies on outdoor air to reject heat, rather than trying to reject that heat in, say, the summertime, it's very hot outside, you need to run your loop very hot to reject any heat from it, you actually run your thermal resources in the winter. So what you'll do is track year-round your total net BTUs going into and out of the ground, and then know whatever that difference between those two is, you will run over the course of an entire year, whenever it's most expedient to do so, whenever temperatures are low enough, you will run this thermal resource, and that will also freeze that thermal drift in place at where it would be in year one. So for an example of this one that we've done, this is an actual thermal energy network. This is a system out in the Rockaways, also currently under construction, our Vernice development. So this is a single pipe ambient loop system. This is a phased build out. So phase one is currently under construction. It's going to be across 10 total phases, a mix of multifamily, low-rise residential, and commercial. And because of the size of these buildings, it's a very cooling dominant system. So what we have in this is spaced out through the phases, 300 tons of dry cooler capacity that will run. So we'll measure the BTUs because it's a thermal energy network. We already need to measure the BTUs anyway. So we'll know our net imbalance of heating and cooling. Over the course of the year, these dry coolers run an adjustable amount of hours, and those will be used to then keep our bore fields from either overheating, well, keep our bore fields from overheating. They're just one way in this case. And that is for this part, and for more on other types of TENS and ways to hybridize them, I'll turn it over to Mike.
Okay. Thank you, Sam, for the introduction into hybrid thermal energy networks. I want to dive a little bit deeper into how we find our way to hybrid systems, especially in terms of the thermal energy networks. The biggest challenge to why we get there is going to be the drilling cost. Second challenge, land constraints, which you heard about a little bit. And the third, which Sam touched on the most, load diversity and thermal imbalance as you move through the system. So I'm going to dive into all those in a minute, but first I got to do the obligatory plug for LaBella Associates. So I work for LaBella Associates. We are 2,000 people, full service architecture engineering. We're 900 in New York State. Our headquarters are in Rochester. And if you are contemplating a thermal energy network, been sitting in this room all day thinking about one, we can maybe help you out. So, and it wouldn't be a geothermal presentation without the cartoonish slide here with the red and blue water, right? So this is a thermal energy network. This is depicting a one-pipe system where we have our bore fields. We have multiple different off-takers here, commercial, residential, buildings that are absorbing heat, rejecting heat, and then also, not to be ignored, but the utilities that we're co-locating the system with over on the left-hand side of the slide. That does become a challenge in some of these. Of course, we want to work towards this type of arrangement. We know about the efficiencies. We know all the benefits of electrified heating systems. But now to address those challenges, the first one being the upfront cost. There is some incentives in place. The tax credit, most notably, to reduce the well field cost, or bore field cost, I'm sorry to keep saying that. When we look at the bore field, we know that it accounts for approximately 40 to 50% of our CapEx when we look at the system as a whole. The incentives help to reduce that cost. You'll see those numbers look low to you because they don't include the bonuses for prevailing wage and apprenticeship. But they do exist, but they are phasing out over time. A second challenge is going to be the limited land area. This is the same slide as I had before, but now we got to think about when we're having a utility scale or just a large thermal energy network, and we need to control the temperature of the water in between all of our buildings, right? So there's been some discussions in this room is how do we monetize the system? What does the building structure look like? Well, if you're going to do that, you're going to have to make sure that the water you deliver to the first building is pretty comparable to the one in the fourth. So you might end up in a situation where you need some sort of heat exchange right in the middle of your loop, and you might not have room to do it. And then the thermal saturation, I won't touch on this too much, but of course this does happen in unbalanced loops where you just, the designer maybe didn't account for it, or maybe the system changed over time. Loads got taken off the system or added, and you end up with your bore field water temperatures kind of running away from you. So the hybrid system, applying different technologies to the traditional bore field model, wastewater, heat exchange being one, aquifer systems, surface water heat exchange, of course, traditional boiler and cooling tower, which was mentioned. I'm going to give a few anecdotes of jobs where we've looked at some of these different methods. This is the first one. This is SUNY Sullivan. This is a community college in the Catskills. I got to this job probably 2017-ish. There was 290 bores, 10 buildings, 143 heat pumps. This system had been in service probably for about 10 years when I got there, and we were able to get the BMS contractor to pull some entering water temperatures into the ground heat exchanger there. And you can see them. It's not perfect. There's some data missing, but if you apply a linear trend line to it, you can see it going up. Part of the reason why this was happening is because this was already a hybrid system, because there was a propane boiler in building H, it's the long skinny one, kind of top right, where they were taking up a lot of the outside air heating loads, as well as some of the perimeter heating loads. So we looked at this, we saw the problem, and just want to encourage everybody to get creative about solutions. So rather than we could have added a dry cooler or cooling tower to this, instead what we did was we took their electric resistance domestic hot water system offline. It was antiquated anyways, and we connected that up to, we used a heat pump to store water in 2 300-gallon tanks. This school did have a pretty robust culinary program, so that load was not insignificant, and it was one way to manage the entering water temperatures into the bore field. Another project, this is a single building, but it's a big one. It's 417,000 square feet. 7,000 MBH heating, 700 tons cooling. This is the Perry Doria office complex. It's out on Long Island. You can see the drill rig in the foreground of the building there, drilling our test well. This has all the traditional components. You see the schematic at the bottom of a hybrid system. When we looked at the loads, and you could see the loads at the top right, you notice how much the cooling loads are compared to the heating loads there. We realized right away the system was going to be cooling dominant. So what we did, of the 700 tons, we installed a 420-ton cooling tower, which removed 160 boreholes and reduced project cost by $2.5 million. Important to note, when we downsized the bore field, we're still able to handle all of the heating load with the ground heat exchanger. So you can see the temperatures there are quite low. That's kind of the extreme case where we've refurbed all the air handling units in the building. They're going to be able to accept the lower temperature heating water. So the heat pumps, in conjunction with the ground heat exchanger, are going to be able to provide all the heating for the building. So then there's a boiler there, and the reason for that is this particular client requires some redundancy, and the boiler was the method that they were the most comfortable with, but I just wanted to point out that it's not necessarily required in this application. During the shoulder seasons, that bore field, which was about 280 tons of capacity, will be able to handle all of that cooling load. So, springtime and fall, we're just running on the bore field. When we get to the peak load, the peak summer months, we are going to introduce the cooling tower into the loop. It's hydraulically separated with a heat exchanger, and that's going to precondition the ground, the water going to the ground, just so that we don't have any unintended consequences, temperatures in that ground loop. Another pretty interesting project. This was a one-off. This was a study, an electric utility company in Tennessee, and they were. Well, there's a developer who's building, and this is up on kind of a mountain with a lake, a 434-home luxury development. So the utility company's involved because they're trying to figure out how to get power up there, right, and cut their loads. And they heard about thermal energy networks and came to us and said, can we commission a study to look at some creative solutions here? And so you can see again, you're going to have a cooling dominant load. 1,500 tons of cooling, 2,000 MBH heating. What we conceptualized here was a series of plate heat exchangers that are suspended off the lake bottom. So there's about 12 in all of 20 plates. And I don't know if can't really see it. It's on the site plan, the little lines going out into the middle of the lake. That's where they are. So they're in the deepest part of the lake. It's 10 acres. It's 30 feet deep. And we size those. We worked with an expert, and we size those for a maximum 1/2 degree per day of temperature drift in the lake under peak conditions. And what that essentially was able to do was cut the size of the bore field in half. So half of the load is handled by the lake, half is by a bore field. The customer also has the option to do a boiler or cooling tower with the remaining load, should they choose. And then finally, here's a utility thermal energy network project. This one's kind of cool because it's in Buffalo, it's downtown, a densely populated urban environment, but this one makes it onto the hybrid presentation because this one's using a wastewater heat exchanger. So in downtown Buffalo, there is excessive brackish groundwater beyond 250 feet. So the well field would have to be even bigger than normal using that kind of depth. We were able to locate a 96-inch combined sanitary and storm sewer main, size some heat exchange, handle the solids, which is a problem unto itself. But aside from that, recover heat from that system. There's 32,000 MBH of thermal capacity in there from a 10,000 GPM average daily flow on the sewer main. You can see that does well exceed the required heating and cooling of the system, but it's going to give the customer some flexibility to expand it in the future, add cooling to some buildings, and increase efficiency. So that's all I have. Thank you very much, and I'm going to turn it over to Joe.
Hey everyone, I'm Joe DiSanto. I'm a project manager with Ramboll. Ramboll has a number of different industries throughout the company, ranging from environment to buildings, water, wastewater, and energy and transportation. I'm in the energy consulting services that focuses on energy efficiency and planning, ranging from building energy efficiency to large central plant and master planning projects. I'll kind of reinforce quite a few concepts that you heard earlier, talk about some feasibility studies and also some projects from Ramboll Global. At SUNY Cortland, this was a feasibility study. We looked at a parametric analysis to look at all different optimizations of different combinations of geothermal and air, different network configurations, and then variations of base versus peak load. So we looked at sizing the heat pumps for a certain percentage of the peak load. So typically 50, 60, or 70% of the peak will cover anywhere from 80 to 95% of the annual load. And then using existing infrastructure boilers or even electric boilers for that remaining peak and last 5 to 10% of the annual. Also looked at different thermal tank storage sizes and, like I said, electric or natural gas peaking equipment. So why Cortland wants a hybrid solution, it was really showed that a mix of air source and ground source helped with borefield imbalance, so taking some of that load off the borefield by using air source, but it also helped reduce the initial capex of the equipment by over 15% with going with just ground source heat pumps. But at the same time, utilizing ground source keeps the OpEx low, so it's a balance of that CapEx and OpEx, so trying to find what that optimization was. But really, it provided the campus a mix of thermal resources that they are willing to try as the system progresses through different implementation phases. So they don't have to be stuck with one or the other as they go through their implementation over a 20, 30-year period. They can see, try out different technologies and see which one really works best for the campus, and they can pivot, on one technology or the other as they progress. The London Underground, this is an existing district in London. It's the Bun Hill district heating system. They utilized an abandoned station and transformed that into a heat extraction. So they were able to use large fans to extract heat from the tunnels, and then they were able to use heat pumps to put that into their existing heating district. I think that expanded the existing network by over 1,600 homes. And then also in the summer months, they can reverse that fan to help cool the subways tunnels. I don't have a ton of information on this one, so I don't know if I'll be able to answer any questions. But then some examples from Denmark. These are all existing districts. Denmark over the years has transformed, from steam-based district heating to lower temperature hot water networks, and now they're implementing heat pumps more readily into their systems. I'm not going to try to pronounce any of these names, but in Odense, there's a metadata center, and they're recovering waste heat from that data center. They also have a wastewater treatment plant there. They're utilizing the effluent as a heat source for heat pumps, but there's also quite a bit of biomass, CHP, some waste energy, industrial waste heat that they're using, and then also combining that with some oil and gas peaking and reserve capacity. In Turnbu, that's the middle one, they're utilizing the wastewater treatment plant again. This is a very large wastewater treatment plant, and it's also helping feed the district cooling network by utilizing heat recovery chillers to provide some of that heating and cooling load. And they also have a groundwater aquifer plan for the future. So all of this is already in operation. And the groundwater aquifer, I think they're looking at an ADAS system. And then on the right is Esbjerg and Aalborg. Esbjerg is actually currently installed and operating. They have seawater heat pumps, very large units that are producing some pretty impressive heating temperatures and some pretty impressive COPs with very low seawater temperatures. I found out today, they had some pretty cold temperatures this winter. I think they had a cutoff of 30 degrees Fahrenheit. I think the water freezes around 29.5, so they deemed that very limited delta T provided small capacity, but it works down to 30 degrees Fahrenheit on the incoming seawater temperature, and they're able to supply 194 degree temperature to the network. But all of these examples, they're using natural refrigerants. ranging from ammonia to carbon dioxide. And that's all I had for examples.
Hi, everyone. Adam Shelly from Ecosystem Energy. I'm very excited. Oh, okay. Sorry. I'm very excited to talk to you about something really interesting, taxes. Right? Isn't this great? We're at a geothermal conference, and now we're talking about taxes. This is amazing. So quickly about Ecosystem and why I'm involved here. We're an integrated engineering and construction company. We have a office in New York, as well as a number of different US cities and Canadian cities where we've been doing heat pumps, some geothermal, and a lot of other technologies for 35 years. We only work in existing infrastructure and distribution networks and production. So we do everything from the development all the way through to startup and commissioning, which I think is critical on these thermal energy networks. A lot of other interesting numbers about Ecosystem, blah, 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 blah. Rockefeller Center is one of Con Ed's U10s that was designed. We are leading the development of that along with WSP and, of course, the Con Ed team. Spoiler, that does not have geothermal, but maybe one day it will when it expands. I just wanted to say that out loud. We're all hopeful that geothermal will be on every project because this is a geothermal conference. Montreal Biodome does have geothermal, proud to say it. This is obviously in Canada, it's in Montreal. It's a very cool place if you ever want to go, but this is the epitome of hybrid. It has a little bit of everything in terms of climates and technologies. So for taxes, first, the ITC, the investment tax credit, expanded with the IRA in 2020. It was modified by the One Big Beautiful Bill Act in 2025. I think that's right. We're going to focus, well, I was here a couple of years ago talking about active thermal energy storage, which is the concept of these thermal energy networks being the storage facilities themselves, therefore qualifying the entire network and everything that was connected to it as thermal energy property, thermal energy storage property. That was a fantastic idea that a few projects harnessed, and then the IRS killed that idea through future modifications of the bill. So good riddance, active thermal energy storage systems, onward hybrid geothermal systems. Everyone knows ITCs, they're calculated through a four-step process. Identify eligible thermal property, identify the eligible cost of that property, confirm the tax rate structure for your system, and then start it all over again multiple times. That's the hybrid nature of it. There's a lot of different calculations that go into this. Some of them are energy-based, some of them are initial cost-based, a lot of them are tax-based, or should be, and we'll get to there, as well as other needs that the end users and utilities and campuses have. So one important feature of the ITC for geothermal is the concept of dual use. It's when a system serves both qualifying and non-qualifying uses. In that scenario, the ITC has to be allocated proportionally. I have a graph, as I'm an engineer, so obviously I have a good graph coming up on what that really means. So some examples in hybrid, if you don't know by now from everyone else. Heating, is it space heating? Is it domestic hot water? Is it borefields? Is it a boiler or a cooling tower? The allocation methods depends on how you're approaching the system. There's a number of different concepts out there that are legally based. I want to reiterate, I'm an engineer. I'm not a lawyer. I'm not an accountant. But I functionally gave myself a JD over the past 3 years. My friends who are lawyers disagree with that fact. But it's important that you need to view this problem through all three lenses. So I think the technical part is pretty much covered at this conference, and I think everyone's doing an excellent job at designing these hybrid systems, at designing geothermal. But what we really need to embrace, some of you have already, is the financial side of that and stacking these incentives. So dual use, how is that impacted in the ITC? based on the system's energy use, if the system itself is deriving energy from geothermal less than 50%, there is no tax credit. So if you have a geothermal field that's doing 20% of the energy for the heat pump or the distribution system, you're going to get $0. Starting at 50%, it jumps up and then goes proportionally between 50% geothermal use and 100%. I'm assuming in this scenario that you are complying with the prevailing wage and you're getting the 30% tax credit. Yes, I know if you don't do prevailing wage and you're above 1 megawatt, it goes down to 6%, but don't do that. That's like, you're leaving money on the table. So I'm assuming that we're all capable of making sure we get the 30%. That's for all the numbers in the rest of this presentation. So if you get under 50% geothermal energy derived, you're going to be very sad. If you get above 50%, you're going to start being happy. This is the one takeaway that I want you to have in terms of hybrid geothermal and how it's going to impact the taxes. It's very, very important. When I was a younger engineer at a consulting firm, I never wanted to talk about money. And then I became a contractor, and we only wanted to talk about money. And now I'm at a company that does both, and we talk about money in appropriate amount. So whoever you are, talk about the money. Here are some of the other sources. I mentioned those already. So I hear a lot in this session that we should optimize for energy savings because thermal energy networks are long-term. That's partially true. But I say no. No, don't just optimize for energy savings. In hybrid geothermal, we optimize for after-tax cost of energy. You have to include the financials here. You have to. So LCOE is levelized cost of energy. That was a big buzz metric for a long time when you're comparing wind to solar to geothermal to energy efficiency projects. But we have to move past that in this era because of the federal tax credits, because of the utility incentives, because of the state tax credits. So when does 2% matter the most? Between 49 and 51%. The difference is between $0 and millions of dollars, and that is not hyperbole. If you mess up this calculation, you will jeopardize your tax credit, and a lot of people will be very, very disappointed with a sad face. Integral to energy property. Why is this important? This is a very layered conversation. A lot of lawyers will eventually get involved in this, and a lot of accountants, a lot of cost segregation. But there's a lot more to this tax credit than just the bore field. It's the bore field, it's the distribution piping, it's the heat pump, and then potentially it's the equipment inside that's connecting to the geothermal. That is a massive, massive swing for projects that have a lot of connected infrastructure going on. Are there any lawyers in the room before I show the next slide? Great. A spectrum of defensibility. So everything that I said until now is definitely true. And now what I'm about to say is something that is subject to opinion, not just my opinion, but between different lawyers and different accountants and different tax credit insurance companies. There's a lot of parties that get involved in these tax credits. If you're direct pay, it's potentially easier. If you're selling your tax credit because you can't monetize it yourself, you're probably going to have to get tax credit insurance, which requires all the other parties involved. So my recommendation is to look at the spectrum of how much you're pushing this tax credit. So at a minimum, the bore fields and the heat pumps qualify. I think everyone would readily agree to that. The distribution piping, it depends. I don't know if everyone agrees with that. It depends on the circumstances. Every one of the projects that we design and implement, we make sure we're putting as much distribution in there that makes sure it's eligible as possible because we want the full 30% on that as well. And then the terminal units is a bit more aggressive. We're working on a building. We're retrofitting the entire building. It's really 2 buildings. And originally we thought we were going to be introducing a number of air source heat pumps as well as the traditional plus geothermal. Really have everything involved in the hybrid. But as we continued talking to the client, who had an aggressive appetite for tax credits, as well as some advisors and lawyers, we felt that the entire inside system, the terminal units in every single room, could qualify as eligible property. That fact and that decision impacted the entire project because it's now 100% geothermal. There is no hybridization there. I'm at a geothermal conference. I was really expecting like a large cheer for that. Like, come on! It's fine. So going back to this graph, I spent a long time doing this. You really want to get all the way up there. Get as high as you can. Work on it. Iterate, iterate, iterate. You will have resistance from people. You will meet conservative people. You will meet people who just think it's the geothermal bore field that qualifies. Everybody's wrong, including me. You have to work with your team. You have to work with your client. You have to work with the lawyers, the accountants, everybody. This is a field that if it's going to really accelerate over the next 7 years or 5 years or however long until 2033 or beyond when that tax credit exists, we've got to learn this and learn to love it or learn to hate it and still do it. I don't really care. But this is where this industry changes. Thank you. And now we'll do questions. I'll hand it back to Diego. This takes you to my LinkedIn page. Feel free to use it, or it might take you to send me Bitcoin, but you'll have to find out.
Thanks, Adam. Always bring in the humor. There you go. All right, so we're going to go ahead and open it up to questions now. And just to reiterate, whenever you do have a question, please state your name and company associated with. Thank you.
Hi, Bob Wyman here. Question, but first just a warning. The IRS holds opinions which I believe are in conflict with some of the things that were said earlier. Be sure to check with your tax attorneys and the IRS before deciding what to do. I'll talk about this more in my session tomorrow. Anyway, the question for this panel.
You can't advertise in our session.
The question for this panel is, there's a problem with hybrid in that the sources of thermal resources are not always co-located with the demand for the thermal resources. It's really easy when you've got, say, housing next to a steel plant. It's a little more difficult when you've got a steel plant or a river, but the houses you want to be cooling or heating are like 10, 15 miles away. Now, the electric industry solves this problem by making a distinction between the transmission grid and the distribution grid. So I'm wondering, while we're talking about TENS, should we also be talking about something that connects TENS, call it an inter-TEN? And what the function of an inter-TEN would be is to distribute thermal resources between TENS. In New York City, for instance, you might have a loop around the entire city which was plugged into the river or plugged into power plants or plugged into whatever. And then individual TENs would be able to supply excess energy to those or pull energy off of the inter-TEN. Does such a structure make sense? Has anybody thought about building one of these, or should we be thinking about building inter-TENs in the future?
By inter-TENs, I think you're talking about like connecting that were previously independent thermal energy networks to each other. They do a lot of that in the Nordic countries. There's a lot of municipalities that have started their own thermal energy networks because they have biomass with wood, or it's waste or just something else. And then they've connected to each other, sort of similar to how cities grow too. So I think that's a model that we're at least looking at, thinking about New York, and we try to plan for it in the designs of these pilots. But obviously we want to make sure that the ratepayers' money is being used wisely, and so we're trying to make sure that one gets off the ground before we start networking all of them.
Yeah, and I'll touch on too, it's a thing that we factor in the design is this ability for future addition and interconnection onto what we are already building. It's a little hard to interconnect the 10s when we haven't built the first one yet, where we're more focusing on trying to get this one built, and we will add in connections, a lot of times whenever we have this central utility plant where that hybrid system is located, you will have blind flange as a spot, and you say, this is where in the future you can put your pumps, this is where you can put that piping connection, this is where you can grab it, should something like that ever be built nearby or other thermal resources become available.
Yeah, in the Denmark example I showed, those cities aren't one network, they're multiple networks. Like Adam was saying, they started out as little individual networks, and eventually they grew to be citywide, where they're covering like 90% of the buildings there. But they are all interconnected. They share loads between each other. And then also, when the thermal source is pretty far away, they have transmission pipes. So they're not running at 150, 160 degree hot water. They're running at 190, 200 degree water to bring them into those city centers.
Hi, my name is Max. I'm with Brightcore Energy. I have a question for Adam. Regarding your tax credit, do you take into account, how do you take into account the heat recovery, and especially with the distribution? Do you?
Heat recovery from like the building itself?
Yeah.
They do not qualify that as geothermal, so that would be another source of energy.
And what if it's a building with heavily heat recovery, such a hospital?
So we do a lot of projects that don't use the investment tax credit, including a lot of heat recovery projects. I think hospitals are often great applications for heat pumps alone, and that wouldn't qualify for the investment tax credit, but it's still a great solution with great economics. Did that answer the question?
Yeah, it just doesn't qualify.
Yeah. We tried, trust me.
Hello, Ben Raff, New York Power Authority. So just a question, I guess, to each of the panel members. I'm assuming with the hybrid thermal energy networks, there's a lot of stakeholder engagement. Wondering if you guys could speak to lessons learned with all the different parties involved.
Yeah, I can start. Lessons learned from the existing systems are, be aware of the amount of training and controls that you're providing on your projects when you're connecting more traditional thermal energy resources like a boiler, right, or a cooling tower to a ground loop. Lots of times there'll be people operating these systems that like to do things the way that they've always done them. You may show up on site and find out you're doing something like heating the ground. We've all heard these anecdotes, right? So I think the training and the communication is important, and just sort of like some sort of continuous commissioning process would be important for these projects.
So I'll say, speaking to working with potential connected clients, a lot of times what we try to do is not necessarily replace their entire system, but be an add-on to what they already have. So they're not, so for example, in some of our pilots that we're exploring, we're working with hospitals, and you don't want to be necessarily, if our system goes down, your whole hospital goes down. So we are, in addition, on top of what they already have, we are another source of redundancy on top of what they have, and just kind of working with them to make sure that we're not becoming a weak link in their system is an incredibly important thing.
I actually think the best group that I know of in this room that could speak to stakeholder alignment is the Con Ed team right in front of you. They've done an incredible job aligning customers, I'll just say customers, a group of stakeholders that have very strong opinions. And I think that you could run a whole workshop on that. But when you're thinking about developing thermal energy networks and getting together a bunch of different stakeholders, I think it's really important to have an honest conversation up front about what they're expecting. Is this a revenue generator for them? Is this a decarb opportunity? Is this a way to reduce initial costs or OpEx in the future? What is their ability to take on risk? Or do they just want to be a customer, or they want to be an owner of that system? So I think really setting a level playing field and getting expectations. I will talk almost about everything to answer your question except for the technical part, because that's really the part that we have the most information about, and in some ways is the easiest part.
Thank you.
Hi, my name is Ellie Kahn from NYSERDA. I had a question about tax credits and how you factored that into some other types of decision making about ownership structures in particular. Like, have you explored energy as a service or P3 models in addition to sort of, single owner models as part of that? And sort of, can you talk about your thought process as you make those types of decisions?
Yes, that is a huge part of the ownership portion, because there are some entities that can't take advantage of the tax credit, or it's not clear exactly how they would monetize it. Sometimes there's misalignment between those parties. The P3 model, I think, has been very heavily used in higher education. That's allowed the operators or the concessionaires in that model to take advantage of those tax credits in ways that a lot of the universities have not been able to. There is, in a lot of the energy as a service models, there's multiple ways to do it, and some companies are leveraging entities that are not taxable, so that they might not be able to take advantage of all the tax credit, but when they go out to get some debt, they're able to get cheaper debt than everyone else, and so that's a benefit to it. So these decisions impact things at the development side of it, absolutely. So it's an industry on its own. They literally have their own conference.
Anyone else? All right, thank you all.
Good job, guys.